The question is, a transformer has a final steady temperature rise of 75 degrees Celsius at full load and a heating time constant of 3 hours. Copper loss at full load is twice the iron loss. Calculate the temperature rise of the transformer at the end of the following load cycle after starting from cold conditions. Full load for 2 hours, no load for 1 hour and 20% overload for 1 hour. So it is given in the question that the final steady temperature rise of the transformer corresponding to full load is 75 degrees Celsius and the heating time constant is 3 hours, and the relation between copper loss and iron loss is given as copper loss at full load is twice the iron loss. So we are asked to calculate the temperature rise of the transformer at the end of the load cycle, and the load cycle is also given. So we can draw the variation of temperature rise with time. The first region indicates the full load portion, that is for 2 hours, so that corresponds to heating. And the second portion corresponds to no load for 1 hour, so that corresponds to cooling. And the third portion is 20% overload for 1 hour, so that corresponds to heating. So first let us consider the first portion of the load cycle, that is full load for 2 hours. So in the question it is given that the final steady temperature rise corresponding to full load is 75 degrees Celsius. So we can write theta m as 75 degrees Celsius, and the initial temperature rise is 0 degrees Celsius as the machine is starting from cold conditions. That is also given in the question. Then the machine is operating on full load for 2 hours. So we can write T small t as 2 hours and the heating time constant TH is 3 hours. So we can calculate the temperature rise at the end of 2 hours. So that will be equal to theta m into 1 minus e raised to minus t by th. So theta m is 75. T is 2 and TH is 3. On substituting, we'll get the temperature rise at the end of 2 hours as 36.5 degrees Celsius. So that is written over here. That is at the end of 2 hours, the temperature rise will be 36.5 degrees Celsius. Now we can move on to the second portion, that is when the machine is on no load for 1 hour. So we know that the final steady temperature rise of the machine, that is theta m, is equal to Q by S lambda. So we can write that theta m is proportional to the total losses. So we have to find the final steady temperature rise at no load. That is not given in the question. So for that we can take this relation theta m is proportional to Q. We can write final steady temperature rise at no load by final steady temperature rise at full load as losses at no load divided by losses at full load. And let us take the iron loss as Wi and the full load copper loss as Wc. The iron loss is the constant loss, so it is equal to Wi. So we can write the final steady temperature rise at no load as losses at no load by losses at full load into final steady temperature rise at full load. And corresponding to no load, there will be only the iron loss. So we can write losses at no load as Wi because since the no load current is negligible, the copper losses at no load will be negligible. So we can neglect the copper loss and we can write losses at no load equal to iron loss only. So losses at no load is equal to Wi and losses at full load is equal to Wi is the iron loss and the full load copper loss is Wc. So losses at full load will be equal to Wi plus Wc into final steady temperature rise at full load, that is given as 75. So we can calculate the final steady temperature rise at no load and we will get that as 25 degrees Celsius. Now we can calculate the temperature rise at the end of the cooling cycle. So that will be equal to theta m into 1 minus e raised to minus t by tc plus theta I into e raised to minus t by tc, where tc is the cooling time constant. Since it is cooling, it will be equal to the cooling time constant, and unless otherwise specified, we can take the cooling time constant as the heating time constant itself. So heating time constant is given as 3 hours, so we can take the cooling time constant also equal to 3 hours. Now the final steady temperature rise at no load we have found out, and that is equal to 25 degrees Celsius, and it is working on no load for 1 hour. It is at no load for 1 hour, so we can write T as 1 hour. And the initial temperature rise, so we have to substitute the initial temperature rise in this expression. So the initial temperature rise at no load will be equal to the final steady temperature rise at the first load cycle, that is at full load. So the final steady temperature rise at full load was 36.5 degrees Celsius, and at the beginning of the no load, the initial temperature rise will be equal to the final steady temperature rise at full load itself. So that will be equal to theta I at cooling will be equal to 36.5 degrees Celsius itself. So we can write theta I as 36.5 degrees Celsius. So substituting all these values will get the temperature rise at the end of no load. So that is equal to 33.2 degrees Celsius. So here the temperature rise will be equal to 33.2 degree Celsius. Now we can move on to the third part, that is when the machine is working on 20% overload for 1 hour. So in that region also we have to find the final steady temperature rise corresponding to 20% overload. For that we can use this expression, and we'll get the final steady temperature rise at 20% overload as losses at 20% overload divided by losses at full load into final steady temperature rise at full load. So when the machine is working at x times the rated load, the copper loss of the machine will be equal to x square times WC, because since the copper loss is the I square R loss, at x times the rated load, the current will also becomes equal to x times the rated current. So the copper loss will be becomes equal to x square times WC. So we can write losses at 20% overload. At 20% overload, we can write the current will be 1.2 times the rated current. So the copper loss will be 1.2 square times the full load copper loss. So we can write the losses at 20% overload as Wi plus 1.2 square WC, and the losses at full load is Wi plus WC. So we can find the final steady temperature rise at 20% overload, and it is given in the question that the copper loss at full load is twice the iron loss. So we can substitute that over here. So we'll get the final steady temperature rise at 20% overload as 97 degree Celsius. So substituting that in this expression, we'll get theta as theta m into 1 minus e raised to t by th plus theta e raised to minus t by th. Substituting all these values in this expression, we'll get theta as 51.3 degree Celsius. So that is the temperature rise at the end of the load cycle. So it is equal to 51.3 degree Celsius. In this portion also, that is in the no load portion also, we are taking this relation WC is equal to 2 times Wi. So the temperature rise at the end of the load cycle will be equal to, we have got that as 51.3 degrees Celsius. So this will be equal to 51.3 degree Celsius.